Archimedes of Syracuse stands among the greatest minds in history, a figure whose contributions to mathematics, physics, and engineering shaped the development of science for centuries. His legacy, spanning across numerous disciplines, remains fundamental to modern scientific thought. Born in the 3rd century BCE in the Greek city-state of Syracuse, Archimedes' intellectual brilliance was evident from an early age. His groundbreaking discoveries in geometry, hydrostatics, and mechanics not only expanded human understanding, but also laid the foundation for fields that would later evolve into integral parts of modern physics and engineering. To understand the importance of Archimedes, one must first appreciate the world in which he lived. Ancient Greece was at the height of its intellectual and cultural influence, producing philosophers, mathematicians, and scientists who sought to explain the natural world through reason and observation. The Greek colonies in Sicily, particularly Syracuse, were centers of economic and military power, often caught in the conflicts between Carthage and Rome. This setting provided Archimedes with both the resources and the challenges that shaped his innovative work. Unlike many of his contemporaries, Archimedes was not solely interested in abstract theories. While he made profound mathematical discoveries, he also had a practical mindset, applying his knowledge to real-world problems. His ability to combine theoretical mathematics with applied science set him apart from other thinkers of his time. From developing weapons to defend his homeland to formulating the principles of buoyancy and levers, Archimedes' work demonstrated a deep understanding of both natural laws and mechanical applications. One of his most famous statements, "Give me a place to stand, and I will move the earth," encapsulates his confidence in the power of leverage, a principle he rigorously studied. His insights into mechanics revolutionized the way people understood forces and motion, paving the way for later advancements in engineering and physics. The study of levers and pulleys, which Archimedes advanced, remains fundamental to mechanical engineering today. Beyond mechanics, Archimedes made remarkable contributions to geometry, calculating areas and volumes with unprecedented precision. His work anticipated integral calculus, a field that would not be formally developed until nearly 2 millennia later by Newton and Leibniz. Through methods such as the method of exhaustion, he approximated the value of pi, with remarkable accuracy, demonstrating an analytical approach far ahead of his time. His treatises on conic sections, spirals, and spheres further solidified his place among the greatest mathematicians of antiquity. Archimedes was also a pioneer in hydrostatics, the branch of physics that studies fluids at rest. His famous principle of buoyancy, discovered while investigating the purity of a golden crown, remains a fundamental concept in fluid mechanics. This discovery, allegedly made during a bath and followed by his exclamation of "Eureka! I have found it!" highlights his keen ability to apply mathematical reasoning to practical problems. His work on floating bodies has had lasting implications, influencing naval architecture, engineering, and even modern physics. Despite his immense intellectual contributions, Archimedes' work was not always appreciated in his time. Much of what is known about him comes from later historians such as Plutarch and Cicero, who documented his life and achievements. While his mechanical inventions were highly regarded, his mathematical theories were often seen as mere curiosities rather than essential knowledge. However, in later centuries, as scholars rediscovered his writings, Archimedes came to be recognized as a true visionary whose ideas transcended the limits of his era. One of the defining aspects of Archimedes' genius was his ability to blend creativity with rigorous logic. Unlike many of his predecessors, who relied on philosophy to explain natural phenomena, Archimedes sought empirical and mathematical proof. This approach influenced the scientific method, which would later become the foundation of modern science. His systematic use of experimentation and deduction exemplifies the intellectual transition from speculative reasoning to evidence-based understanding. Archimedes' influence extends far beyond the ancient world. During the Renaissance, his works inspired thinkers such as Galileo Galilei, who built upon his insights in mechanics. Later, Isaac Newton's laws of motion and gravity echoed many of the principles Archimedes had first explored. His ability to see the underlying mathematical principles governing the physical world helped bridge the gap between ancient and modern science. ensuring his legacy as one of history's greatest intellects. Archimedes of Syracuse was more than just a mathematician or an engineer. He was a visionary whose discoveries laid the groundwork for numerous scientific advancements. His contributions to mathematics, mechanics, and hydrostatics continue to shape modern scientific disciplines. As one of the most brilliant minds of antiquity, his legacy endures, reminding us of the timeless power of human curiosity and ingenuity. The life of Archimedes began in the Greek city-state of Syracuse, a thriving center of commerce and culture on the island of Sicily. Born around 287 BCE, Archimedes belonged to an era when Greek civilization was at its intellectual peak. While much of his early life remains shrouded in mystery, historical records suggest that he was the son of Phidias, an astronomer. This familial connection to the study of celestial bodies likely played a role in shaping Archimedes' curiosity and passion for scientific inquiry. Growing up in a city that was both a political and military power, he would have been exposed to the engineering marvels and strategic challenges that later influenced his contributions to mechanics and warfare. Syracuse, under the rule of King Hiero II, enjoyed prosperity and strong ties with other Greek states, particularly Alexandria in Egypt, which was the intellectual hub of the Mediterranean. The city was home to a blend of Greek and indigenous Sicilian influences, creating a rich cultural and scientific environment. As a young boy, Archimedes would have encountered mathematicians, engineers, and philosophers who contributed to the intellectual atmosphere of the time. This environment fostered his early exposure to mathematical theories and mechanical innovations, setting the stage for his future achievements. Like many Greek scholars of his time, Archimedes is believed to have traveled to Alexandria for his education. The city housed the famous Library of Alexandria, which contained an extensive collection of manuscripts and texts from all over the known world. There, Archimedes would have studied under the influence of the greatest mathematicians of his time, including Euclid, whose works on geometry were foundational to ancient mathematics. The teachings of Euclid, particularly the elements, provided Archimedes with a systematic framework for his later discoveries in geometry and calculus. During his time in Alexandria, Archimedes was likely exposed to a variety of scientific disciplines, including astronomy, physics, and engineering. The city's intellectual climate encouraged the exchange of ideas among scholars from different backgrounds. This interaction would have introduced Archimedes to the latest mathematical techniques and scientific concepts, which he later expanded upon. He also formed close relationships with other scholars, such as Eratosthenes, who measured the circumference of the Earth, and Conon of Samos, an astronomer and mathematician. These intellectual exchanges contributed to Archimedes' comprehensive understanding of the natural world. While Alexandria provided Archimedes with a strong foundation in mathematics and science, his return to Syracuse marked the beginning of his independent research and innovations. Unlike many of his contemporaries who remained in academic institutions, Archimedes chose to apply his knowledge to practical problems in his homeland. His ability to merge theoretical mathematics with real-world applications became one of his defining characteristics. This approach distinguished him from other Greek thinkers, who often focused purely on abstract mathematical theories without considering their practical implications. Upon returning to Syracuse, Archimedes gained the support of King Hiero II, who recognized his extraordinary intellect. The king often sought Archimedes' counsel on engineering and military matters, leading to the development of numerous inventions that would later prove crucial in the defense of Syracuse. This royal patronage allowed Archimedes to conduct experiments and design mechanical devices, further advancing his contributions to science and engineering. Under Hiero's rule, Syracuse became a center for technological innovation, with Archimedes at the heart of its scientific advancements. Despite his involvement in engineering and applied sciences, Archimedes remained devoted to pure mathematics. Unlike many engineers of his time, who focused solely on practical applications, he explored abstract mathematical concepts with equal passion. His work in geometry, particularly in the study of curves, volumes, and areas, demonstrated his unparalleled ability to manipulate mathematical principles. His contributions to calculus, although not fully recognized until centuries later, showcased his deep understanding of infinitesimals and limits, which would later form the foundation of modern mathematical analysis. One of the remarkable aspects of Archimedes' intellectual pursuits was his ability to think beyond the constraints of his era. While many Greek mathematicians were content with refining existing theories, Archimedes sought to push the boundaries of knowledge. His curiosity and determination led him to discover principles that would not be fully understood or appreciated until the Renaissance and the scientific revolution. This forward-thinking approach established him as one of the greatest minds of antiquity, whose work continues to influence scientific thought to this day. Archimedes' education and early experiences laid the groundwork for his later achievements in mathematics, physics, and engineering. His exposure to the teachings of Euclid, his interactions with fellow scholars in Alexandria, and his return to Syracuse all contributed to his intellectual development. By combining rigorous mathematical reasoning with practical experimentation, he set a precedent for future scientists and engineers. His ability to bridge the gap between theory and application remains a defining characteristic of his legacy. The early life and education of Archimedes played a crucial role in shaping his contributions to science and mathematics. His formative years in Syracuse and Alexandria provided him with a strong intellectual foundation, while his return to his homeland allowed him to apply his knowledge in innovative ways. Mathematics in ancient Greece was a flourishing field, driven by intellectual curiosity and a desire to understand the fundamental principles governing the universe. By the time Archimedes emerged as one of its foremost thinkers, Greek mathematics had already been shaped by the contributions of figures such as Pythagoras, Euclid, and Eudoxus. These mathematicians laid the foundation for geometry, number theory, and logical reasoning, which Archimedes would later refine and expand. His mathematical achievements did not emerge in isolation. Rather, they were built upon centuries of accumulated knowledge and, in turn, influenced the future trajectory of mathematics. One of the most significant influences on Archimedes was Euclid of Alexandria, who compiled the Elements, a collection of mathematical knowledge that systematically organized geometry and number theory. Euclid's deductive approach to mathematics, which relied on axioms and rigorous proofs, became the standard method of mathematical reasoning. Archimedes adopted this rigorous approach, but unlike Euclid, who primarily focused on geometry, Archimedes sought to apply mathematical principles to physical phenomena. This fusion of pure and applied mathematics set him apart from many of his contemporaries. Another key influence was Eudoxus of Cnidus, who developed the method of exhaustion, an early form of integration used to determine areas and volumes of geometric figures. This technique was crucial for Archimedes, as it allowed him to make precise calculations about curved surfaces and irregular shapes. Archimedes improved upon Eudoxus' methods, using them to approximate the value of pi, and derive formulas for the volume and surface area of spheres and cylinders. His work in this area would later be recognized as a precursor to integral calculus. In addition to refining existing mathematical techniques, Archimedes introduced his own innovative approaches. He was one of the first mathematicians to use the concept of infinity in a systematic way. While Greek mathematics traditionally avoided the idea of infinity due to philosophical concerns, Archimedes developed ways to work with infinitely small quantities. His approach to infinitesimals anticipated modern calculus, demonstrating a deep understanding of the limits of mathematical precision. One of Archimedes' greatest mathematical achievements was his work on pi symbol. Prior to his discoveries, mathematicians had estimated pi using rudimentary techniques. Archimedes, however, used an ingenious method involving inscribed and circumscribed polygons to approximate its value. By calculating the perimeters of these polygons, he established that pi was between 3.1408 and 3.1429, an astonishingly accurate estimate for his time. His method remained the most precise way to approximate pi for nearly 1,500 years. Archimedes also contributed significantly to combinatorics and number theory. His treatise, The Sand Reckoner, sought to calculate the number of grains of sand that could fit inside the known universe. In doing so, he devised a system for expressing extremely large numbers, challenging the conventional Greek numeral system. This work demonstrated his ability to think on a grand scale, applying mathematical reasoning to seemingly impractical problems. His methods for dealing with large numbers foreshadowed the development of modern scientific notation. Another area in which Archimedes excelled was geometrical analysis. His studies on spirals, parabolas, and centers of gravity introduced new ways of understanding curves and forces. In his work on spirals, he described the mathematical properties of the Archimedean spiral, a curve that has since found applications in engineering, physics, and even art. His analysis of centers of gravity, found in his treatise on the equilibrium of planes, was an early step toward the development of statics, the branch of mechanics that deals with forces in equilibrium. Archimedes' impact on mathematics was not confined to theoretical studies. His discoveries had practical implications as well. His work on levers and buoyancy, which will be discussed in later chapters, was grounded in mathematical reasoning. He applied geometric principles to mechanics, demonstrating the interconnectedness of mathematics and physical reality. This approach influenced later scientists, including Galileo and Newton, who built upon his findings in their own work. Despite his monumental contributions, many of Archimedes' mathematical works were nearly lost to history. His manuscripts, written on papyrus and parchment, were copied and recopied over the centuries, often suffering damage and neglect. Some of his most important writings, such as the method of mechanical theorems, were only rediscovered in the 20th century through the analysis of the Archimedes palimpsest, a manuscript that had been erased and overwritten with a Christian text. This rediscovery highlighted the depth of his insights and reaffirmed his status as a mathematical pioneer. Archimedes was not merely a product of Greek mathematics. He was one of its greatest innovators. He built upon the work of Euclid and Eudoxus, refined the method of exhaustion, introduced advanced techniques for dealing with infinity, and made groundbreaking contributions to geometry, calculus, and number theory. His ability to bridge pure mathematics with real-world applications set a precedent for future scientists and mathematicians. Archimedes' contributions to geometry represent some of the most significant advancements in ancient mathematics. His ability to analyze and calculate areas, volumes, and surface properties of complex shapes set him apart from his predecessors. Long before the formal development of calculus, Archimedes devised methods that closely resembled integral calculus, allowing him to solve problems that would remain unsurpassed until the work of Isaac Newton and Gottfried Wilhelm Leibniz in the 17th century. His mathematical genius was not only theoretical, but also practical, influencing later developments in engineering, physics, and astronomy. One of Archimedes' greatest achievements in geometry was his work on curved surfaces and volumes. While earlier Greek mathematicians had focused primarily on straight-edge polygons and simple three-dimensional solids, Archimedes extended these studies to curved figures such as spheres, cones, and cylinders. In his treatise on the sphere and cylinder, he derived formulas for the surface area and volume of these shapes, proving that the volume of a sphere is 2/3 that of the smallest cylinder in which it can fit. This discovery was so important to him that he requested it be engraved on his tombstone, demonstrating the pride he took in his geometric work. Another major contribution was his pioneering use of the method of exhaustion, a technique that allowed him to approximate areas and volumes with remarkable accuracy. This method involved inscribing and circumscribing polygons around a given shape, calculating their areas, and using a limiting process to approach the actual value. This technique was an early form of integration and laid the groundwork for later developments in calculus. His ability to systematically refine estimates of complex shapes allowed him to push the boundaries of mathematical knowledge beyond what was previously possible. One of Archimedes' most famous applications of this method was his calculation of the value of pi symbol. Recognizing the difficulty of determining the exact value of pi, he used inscribed and circumscribed polygons with increasing numbers of sides to approximate it. Through this method, he established that pi lay between 3.1408 and 3.1429, an approximation that remained the most precise for over 1,000 years. His work on pi demonstrated not only his mathematical ingenuity, but also his ability to apply abstract techniques to solve practical problems, such as measuring circular objects accurately. Archimedes also made significant progress in the study of spirals and parabolas. In his work on spirals, he examined the properties of a curve that now bears his name, the Archimedean spiral. This spiral, which describes the path of a point moving at a constant speed away from a central point while the entire figure rotates at a constant rate, has applications in engineering, physics, and even biological growth patterns. His analysis of this curve demonstrated his ability to blend geometry with motion, anticipating concepts that would later become central to kinematics and dynamics. His treatise Quadrature of the Parabola showed his mastery of approximating curved areas. In this work, he calculated the area under a parabolic segment by summing an infinite geometric series. By proving that the total area was equal to 4/3 of a certain inscribed triangle, he effectively demonstrated an early form of integral calculus. This achievement was particularly impressive because it showed that Archimedes had developed a systematic approach to dealing with infinite sums, an idea that would not be formally incorporated into mathematics until the development of modern calculus. Another remarkable aspect of Archimedes' work in geometry was his understanding of center of mass and equilibrium. His treatise on the equilibrium of planes introduced fundamental principles that would later influence physics and engineering. He studied the balance of geometric shapes and calculated their centers of gravity, providing insights into how objects remain stable or fall over when subjected to external forces. His work in this area foreshadowed the later development of statics, a branch of mechanics that deals with forces and equilibrium. Despite the revolutionary nature of his discoveries, Archimedes often downplayed the practical applications of his work, considering pure mathematics to be the highest intellectual pursuit. However, his ideas would go on to influence countless scientists and engineers. The rediscovery of his works during the Renaissance sparked new interest in mathematics and physics, inspiring figures such as Galileo Galilei, who admired Archimedes' approach to mathematical reasoning and experimental science. One of the most fascinating aspects of Archimedes' mathematical work is how much of it was nearly lost to history. Many of his manuscripts were copied and recopied over the centuries, with some being erased and overwritten with religious texts. The Archimedes palimpsest, a medieval parchment that contained hidden mathematical writings, was rediscovered in the 20th century, revealing previously unknown insights into his thought processes. These rediscovered works confirmed that Archimedes had developed concepts that predated modern calculus by nearly 2 millennia, cementing his status as one of the greatest mathematical minds of all time. Archimedes' breakthroughs in geometry and calculus-like methods were far ahead of his time. His ability to calculate areas and volumes, his approximation of pi, his analysis of spirals and parabolas, and his work on centers of gravity all contributed to the mathematical and scientific advancements that followed. His use of infinitesimals and limits paved the way for integral calculus, and his systematic approach to solving geometric problems influenced generations of mathematicians. Among the many contributions of Archimedes to science, his discovery of the principle of buoyancy remains one of the most celebrated. This principle, often referred to as Archimedes' principle, describes how objects behave when submerged in a fluid and provides the fundamental explanation for flotation. His work in hydrostatics, the study of fluids at rest, not only laid the foundation for modern fluid mechanics, but also had immediate practical applications in engineering, naval architecture, and industry. This discovery, according to historical accounts, stemmed from a problem posed by King Hiero II of Syracuse and led to the famous anecdote of Archimedes exclaiming, "Eureka!" after realizing the solution. The problem presented to Archimedes involved determining whether a golden crown commissioned by King Hiero II was made of pure gold, or if the goldsmith had secretly replaced some of the gold with a cheaper metal such as silver. The challenge was that the crown could not be damaged or melted down for analysis. At the time, there was no direct method for measuring the exact composition of a solid object without altering its structure. The solution required a novel approach that combined physics and mathematics in an unprecedented way. According to tradition, Archimedes discovered the principle while taking a bath. As he submerged himself in the water, he noticed that the amount of water displaced seemed to correspond to the volume of his body. This realization led him to formulate what is now known as Archimedes' principle, which states that an object submerged in a fluid experiences an upward buoyant force equal to the weight of the fluid it displaces. This principle explained why some objects float while others sink, and provided a means of measuring the volume of irregularly shaped objects, such as King Hiero's crown, by measuring how much water they displaced. Applying this discovery, Archimedes devised a clever experiment to test the purity of the crown. He compared the water displacement caused by the crown with that caused by an equal weight of pure gold. If the crown displaced more water than the pure gold, it indicated that it had a larger volume and therefore must contain a less dense metal, such as silver. The experiment confirmed that the crown was not pure gold, exposing the goldsmith's fraud. This successful application of physics to solve a real-world problem demonstrated Archimedes' exceptional ability to bridge theory with practical investigation. Beyond this specific experiment, Archimedes' work in hydrostatics had profound implications. His principle of buoyancy became essential in naval architecture, as it allowed shipbuilders to calculate whether a vessel would float or sink based on its displacement of water. This understanding helped optimize the design of ships and submarines, leading to improvements in maritime travel and military defense. Even today, the same principles are used in engineering applications such as designing submarines, measuring fluid density, and determining the stability of floating structures. Archimedes also studied fluid equilibrium, introducing concepts that would later become fundamental to fluid mechanics. He examined how pressure was distributed in a fluid at rest, developing ideas about hydrostatic pressure that would influence later scientists such as Blaise Pascal and Daniel Bernoulli. His insights allowed for a better understanding of hydraulics, leading to advancements in irrigation, water transport, and hydraulic engineering. Although he did not have access to modern measuring tools, his theoretical approaches were remarkably accurate and paved the way for future discoveries in fluid dynamics. Another important concept explored by Archimedes was specific gravity, which refers to the density of a substance relative to the density of water. By comparing the weights of objects in air and in water, he developed a method for determining their densities and compositions. This technique had significant applications in metallurgy, allowing ancient artisans and traders to assess the quality of precious metals. The ability to distinguish between materials based on their density played a crucial role in economic and technological developments in the ancient world. Despite the practical implications of his discoveries, Archimedes regarded his work in hydrostatics primarily as an intellectual pursuit rather than an effort to advance technology. Like many Greek mathematicians, he was more interested in the theoretical elegance of his findings than their utilitarian benefits. However, history has shown that his principles became indispensable in various fields, from engineering to medicine. For example, modern hydrodynamic principles, which rely on Archimedes' discoveries, are essential in designing everything from pipelines to aerospace vehicles. The influence of Archimedes' principle extended far beyond his lifetime. Renaissance thinkers such as Leonardo da Vinci and Galileo Galilei revisited his work, refining and expanding upon his theories. His hydrostatic principles also played a crucial role in the scientific revolution, influencing the development of fluid mechanics and thermodynamics. The legacy of his discoveries continues to shape engineering, architecture, and even environmental science, where buoyancy calculations are essential in studying ocean currents and atmospheric pressure systems. Archimedes' discovery of the principle of buoyancy was a milestone in the history of physics and engineering. His work in hydrostatics laid the groundwork for fluid mechanics, naval architecture, and various scientific applications that remain relevant today. Through a combination of observation, experimentation, and mathematical reasoning, he solved a problem that had confounded his contemporaries and, in doing so, provided one of the most enduring principles of physics. Archimedes was not only a brilliant mathematician and physicist, but also a pioneer in the field of mechanics. His studies of levers, pulleys, and simple machines revolutionized the understanding of force and motion, laying the groundwork for classical mechanics. By applying mathematical principles to practical problems, he was able to develop innovations that enhanced construction, warfare, and everyday labor. His mechanical discoveries had profound implications, influencing engineering and physics for centuries to come. One of the most famous contributions of Archimedes to mechanics was his formulation of the law of the lever. His studies demonstrated that a lever could amplify force, allowing a small effort to lift a much heavier load. He famously stated, "Give me a place to stand, and I will move the earth," illustrating the power of levers when properly applied. His mathematical analysis of levers showed that the force needed to lift an object depends on the distance from the fulcrum, an insight that remains fundamental to engineering and physics. Archimedes extended this principle to pulleys and compound pulley systems, which allowed for even greater mechanical advantage. According to historical accounts, he demonstrated the effectiveness of pulleys by single-handedly moving a large ship using a system of ropes and wheels. The ability to lift heavy objects with minimal effort had significant practical applications, particularly in construction and naval engineering. His discoveries helped improve cranes, hoists, and other lifting devices that were crucial in building large structures and transporting materials. In addition to these simple machines, Archimedes studied the properties of screws and wedges, further developing their mechanical applications. One of his most famous inventions, the Archimedean screw, was designed to transport water from a lower level to a higher one. This device, which consists of a helical blade inside a cylindrical tube, was originally used for irrigation and drainage, but later found applications in mining, agriculture, and even modern machinery. The Archimedean screw remains in use today, demonstrating the enduring value of his engineering principles. Beyond these fundamental mechanical devices, Archimedes also explored the concept of center of gravity, which is crucial in understanding balance and stability. His studies on equilibrium allowed him to calculate the centers of mass for various geometric shapes, providing insights into how objects behave under the influence of gravity. These discoveries were later used in structural engineering, enabling architects and builders to design more stable structures. His work laid the foundation for the field of statics, which deals with forces in equilibrium. Archimedes' mechanical innovations were not limited to peaceful applications. They also played a vital role in military defense. During the siege of Syracuse, 214 to 212 BC, he devised a series of war machines that helped the city resist the Roman army for years. These included catapults, large cranes capable of overturning enemy ships, and even purported devices that could focus sunlight to set ships on fire, although the historical accuracy of this last invention remains debated. Regardless, his military engineering significantly delayed the Roman conquest of Syracuse and showcased his ability to apply scientific principles to real-world challenges. One of his most intriguing military inventions was the claw of Archimedes, also known as the Iron Hand. This device was reportedly used to defend Syracuse's coastline by lifting and capsizing enemy ships. Operated by a system of levers and pulleys, the claw could seize a Roman vessel and overturn it into the sea. The ingenuity behind this machine demonstrated Archimedes' deep understanding of mechanical advantage and his ability to apply it in creative ways. Although many of Archimedes' mechanical works were lost over time, his ideas continued to influence later scientists and engineers. His principles of levers and pulleys became foundational to mechanical physics, inspiring Renaissance thinkers such as Leonardo da Vinci and Galileo Galilei. Galileo, in particular, admired Archimedes and expanded upon his theories, further developing the study of motion and mechanics. The influence of Archimedes extended well into the scientific revolution, shaping the works of Newton and other key figures in physics. Despite his extraordinary contributions to mechanics, Archimedes viewed himself primarily as a mathematician rather than an engineer. He considered his mechanical inventions to be secondary to his theoretical discoveries in geometry and physics. Nevertheless, his ability to combine pure mathematical reasoning with practical problem-solving made him one of history's greatest engineers. His work laid the foundation for modern mechanics, demonstrating the power of scientific inquiry in both theoretical and applied contexts. Archimedes' contributions to mechanics revolutionized the understanding of force, motion, and equilibrium. His work on levers, pulleys, screws, and center of gravity had profound applications in construction, engineering, and warfare. His inventions, from the Archimedean screw to advanced war machines, showcased his ability to apply mathematical principles to solve practical problems. Although he preferred theoretical pursuits, his mechanical discoveries left a lasting legacy, shaping the fields of physics and engineering for centuries. The final years of Archimedes' life were marked by one of the most dramatic conflicts of the ancient world, the Siege of Syracuse, 214 to 212 BCE. This prolonged military engagement between the Roman Republic and the Greek city of Syracuse became legendary due to Archimedes' ingenious defensive innovations, which successfully delayed the inevitable Roman conquest. Despite his preference for theoretical mathematics, Archimedes found himself at the center of war, using his scientific knowledge to create weapons and fortifications that protected his homeland. His role in this conflict solidified his reputation as one of the most brilliant minds of antiquity. The siege was part of the larger Second Punic War, 218 to 201 BCE, during which Rome sought to expand its dominance over the Mediterranean. Syracuse, under the rule of King Hiero II, had historically maintained a peaceful alliance with Rome. However, after Hiero's death, his successor, Hiero III, shifted alliances toward Rome's enemy, Carthage. This decision led Rome to take military action, launching a naval and land assault against Syracuse in 214 BCE. The Roman forces, led by the experienced generals Marcus Claudius Marcellus and Appius Claudius Pulcher, expected a swift victory. What they did not anticipate, however, was the formidable resistance engineered by Archimedes. Although Archimedes had spent most of his life devoted to pure mathematics, he was called upon to apply his expertise in mechanics and engineering to Syracuse's defense. The war machines he designed played a crucial role in holding back the Roman siege for more than 2 years. His knowledge of levers, pulleys, and projectile motion allowed him to create devastating weapons that kept the Romans at bay. One of his most effective contributions was the improved catapult, which launched massive stones and projectiles at enemy ships and troops, causing significant damage before they could approach the city walls. Perhaps the most famous of Archimedes' war machines was the Claw of Archimedes, also known as the Iron Hand. This device, mounted on the walls of Syracuse, used a system of levers and pulleys to seize and lift enemy ships out of the water, shaking them violently or capsizing them entirely. The sight of these enormous mechanical arms lifting ships from the sea reportedly terrified Roman sailors and made direct naval assaults on the city extremely dangerous. This invention demonstrated Archimedes' deep understanding of physics and mechanical advantage, turning his theoretical studies into a formidable tool of war. Another legendary weapon attributed to Archimedes is the death ray, or burning mirrors. According to some historical sources, including later accounts from Byzantine writers, Archimedes devised a method of setting Roman ships on fire by focusing sunlight with an array of mirrors or polished bronze shields. While the effectiveness of this device has been debated, modern experiments have produced mixed results. It remains one of the most fascinating stories associated with his genius. Whether or not it was a real weapon, the idea reflects Archimedes' capacity for innovative problem-solving in warfare. Despite these extraordinary defensive measures, the Roman siege persisted. Over time, the overwhelming military strength of Rome gradually wore down Syracuse's resistance. After more than 2 years of failed assaults, the Romans finally managed to breach the city walls in 212 BCE, reportedly by taking advantage of a festival celebration during which the Syracusan defenses were left vulnerable. Once inside, the Roman army unleashed destruction upon the city, killing many of its inhabitants and plundering its treasures. Syracuse, one of the greatest centers of Greek culture and learning, fell into Roman hands. During the sack of the city, Archimedes met his tragic end. The most widely accepted account, recorded by the Roman historian Plutarch, states that despite orders from General Marcellus to capture Archimedes alive, he was killed by a Roman soldier. According to legend, the elderly mathematician was so absorbed in his mathematical studies that he ignored a soldier's commands, leading to his execution on the spot. Some versions of the story claim that he was working on a geometric diagram in the sand when he was struck down, uttering the famous last words, "Do not disturb my circles." This phrase has since become a symbol of intellectual dedication, representing the unwavering pursuit of knowledge even in the face of violence and chaos. The death of Archimedes was deeply regretted by Marcellus, who had hoped to spare the great scholar. Recognizing his immense contributions to science and engineering, Marcellus allegedly arranged for Archimedes to receive an honorable burial. According to tradition, Archimedes had requested that his tomb be marked with a sphere inscribed within a cylinder, commemorating his mathematical proof that the volume of a sphere is 2/3 that of its surrounding cylinder. This request highlights the deep pride he took in his mathematical achievements, considering them more important than his inventions of war. Despite the destruction of Syracuse, the legacy of Archimedes was not lost. Roman scholars and engineers studied his writings, ensuring that his discoveries were preserved and disseminated throughout the ancient world. His works were later translated into Latin and Arabic, influencing medieval and Renaissance thinkers who expanded upon his ideas. In particular, his principles of mechanics, geometry, and hydrostatics played a vital role in the development of modern physics and engineering. The fall of Syracuse marked the end of an era, but it also marked the beginning of Archimedes' influence on future generations. The Siege of Syracuse was a defining moment in the life of Archimedes, demonstrating both his intellectual genius and the tragic consequences of war. His defensive machines prolonged the resistance of his city, showcasing the practical applications of his scientific discoveries. However, despite his contributions to military strategy, he remained devoted to pure mathematics until his final moments. His death at the hands of an invading soldier was a loss not only for Syracuse but for the entire world of science and philosophy. The legacy of Archimedes has transcended centuries, influencing fields ranging from mathematics and physics to engineering and astronomy. Although his death in 212 BCE during the Siege of Syracuse marked the end of an era for Greek science, his ideas lived on through the preservation of his works and the continued study of his theories. The survival and dissemination of Archimedes' ideas were pivotal in shaping the trajectory of scientific thought, particularly during the Roman, Islamic, and Renaissance periods. Archimedes' contributions became the foundation for many later advancements in science, and his influence can still be felt in modern research and technology. Archimedes' works were not immediately disseminated beyond the Mediterranean world, but his reputation as a brilliant thinker spread through the Greek and Roman intellectual circles. During his lifetime, Archimedes wrote extensively on a wide range of subjects, including geometry, mechanics, hydrostatics, and number theory. However, many of his writings were lost, and the manuscripts that survive were often incomplete or fragmented. The preservation of Archimedes' works can be attributed to the efforts of later scholars, especially during the Roman Empire and the Middle Ages, when his writings were studied, copied, and translated. One of the key figures in preserving Archimedes' works was the Roman scholar Vitruvius, a military engineer and architect who admired Archimedes' contributions to mechanics. Vitruvius's writings, particularly his treatise De Architectura, included references to Archimedes' principles of levers, pulleys, and water screws, ensuring that the great mathematician's ideas were passed down to subsequent generations of Roman engineers. Although Archimedes himself was not fully embraced by Roman scholars at the time, his mechanical innovations continued to influence the construction of Roman buildings and military technologies. In the Islamic Golden Age, 8th to 13th centuries, Archimedes' influence flourished. Scholars of the Islamic world made significant efforts to translate Greek works into Arabic, and many of Archimedes' treatises were among the most prized texts. Figures like Al-Khwarizmi, Al-Battani, and Ibn al-Haytham studied Archimedes' work in geometry, optics, and mechanics, refining his ideas and integrating them into their own advancements in mathematics and science. These scholars also sought to preserve Archimedes' works by copying and disseminating his texts throughout the Islamic world, where they would be studied for centuries to come. One of the most notable examples of Archimedes' work surviving through the centuries is the Archimedes palimpsest, a manuscript that contains some of the oldest known copies of Archimedes' writings. Discovered in 1906, the palimpsest is a medieval manuscript that contains the erased texts of earlier works, including several of Archimedes' most significant treatises. Among the writings found in the palimpsest were Archimedes on floating bodies and the measurement of a circle, which had been lost to history for many centuries. The rediscovery of these texts was a major breakthrough for scholars studying ancient Greek science and mathematics. In the Renaissance, 14th to 17th centuries, Archimedes' influence was revitalized. The Renaissance was a period of intellectual rebirth, during which European scholars began to rediscover and study classical Greek and Roman texts. Archimedes' works, many of which had been preserved by Islamic scholars, played a significant role in this revival of learning. Scholars such as Nicholas Copernicus, Galileo Galilei, and Johannes Kepler drew inspiration from Archimedes' principles, particularly his ideas about the structure of the universe, motion, and mechanics. Copernicus' heliocentric model of the solar system, for instance, was influenced by Archimedes' understanding of the geometry of spheres, while Galileo's work in mechanics built upon Archimedes' discoveries in the field of motion. The invention of the printing press in the 15th century made the dissemination of Archimedes' works easier and more widespread. Scholars in Europe began to print editions of Archimedes' complete works, making them accessible to a broader audience of mathematicians, engineers, and philosophers. The availability of Archimedes' treatises in print contributed to the further development of scientific thought in the Enlightenment and beyond, establishing him as one of the most important figures in the history of science. The works of Archimedes served as both a foundation and a source of inspiration for the scientific revolution that took place in Europe during the 16th and 17th centuries. Archimedes' influence was not limited to the ancient and medieval periods. His legacy has continued to shape modern scientific and engineering advancements. In the field of fluid dynamics, Archimedes' principle of buoyancy remains a cornerstone of modern physics. His work on the hydrostatic properties of fluids influenced the development of Pascal's principle and Bernoulli's theorem, both of which are fundamental to our understanding of the behavior of fluids in motion. Archimedes' work on the lever laid the groundwork for later developments in the study of mechanical advantage, and his theories of center of gravity and equilibrium continue to inform modern engineering practices. Archimedes' impact is also evident in the development of computer science. In the 20th century, the mathematician John von Neumann was influenced by Archimedes' work on algorithms and calculations, particularly his methods for approximating pi and solving problems involving infinite series. Archimedes' innovative use of geometry and algebraic techniques laid the foundation for later developments in computational mathematics, which continue to shape the field of computer science today. Archimedes' legacy has endured through the ages, thanks to the efforts of scholars in antiquity, the Middle Ages, and the Renaissance who preserved and expanded upon his work. His contributions to mathematics, mechanics, and fluid dynamics continue to shape modern science and technology. From the preservation of his treatises in the Islamic world to the Renaissance revival of his ideas, Archimedes' influence can be seen in the foundational principles of numerous scientific fields. His intellectual legacy remains a testament to the power of inquiry and the enduring relevance of scientific discovery. Archimedes' contributions to mathematics, physics, and engineering are not confined to the annals of ancient history. His work continues to inspire and influence modern science and technology, making him one of the most enduring figures in the development of scientific thought. The relevance of Archimedes' principles can be seen in the continuing advancements in various fields, from the study of fluid dynamics and mechanics to the development of computational mathematics and space exploration. The ways in which his ideas have been adapted and applied in contemporary science illustrate the timelessness of his intellect. One of the most significant areas where Archimedes' influence remains strong is in the field of fluid dynamics. Archimedes' principle of buoyancy, often simply referred to as Archimedes' principle, states that an object submerged in a fluid experiences an upward force equal to the weight of the fluid displaced by the object. This simple yet profound insight continues to serve as a foundation for much of modern physics and engineering. It is used in designing ships, submarines, and airplanes, as well as in understanding natural phenomena, such as the movement of oceans and the behavior of gases in the atmosphere. Archimedes' work in hydrostatics also paved the way for the development of important theories in fluid mechanics, such as Pascal's principle and Bernoulli's theorem, both of which are crucial in understanding the movement of fluids and gases in motion. In the field of mechanics, Archimedes' study of levers, pulleys, and simple machines laid the groundwork for classical mechanics. His principle of the lever, which states that the ratio of forces exerted by the two arms of the lever is equal to the ratio of the distances from the fulcrum, continues to influence engineering and design. Modern applications of this principle can be found in everything from the construction of bridges and buildings to the functioning of mechanical devices like cranes and lifts. The concept of mechanical advantage that Archimedes introduced has been crucial in the development of heavy machinery and is integral to the operation of countless modern devices, from vehicles to industrial equipment. Another important area where Archimedes' influence can be seen is in the study of astronomy and space exploration. Archimedes was one of the earliest thinkers to apply mathematical principles to celestial bodies, and his work on the geometry of spheres and circles directly influenced later astronomers and mathematicians. His methods of approximating pi, as well as his understanding of the structure of the universe, laid the groundwork for the development of later astronomical models. For example, Archimedes' approach to calculating the volume of a sphere directly informed the work of later scientists, including Copernicus and Galileo, whose studies of planetary motion were shaped by the mathematical principles that Archimedes had developed. The impact of Archimedes' work on celestial mechanics can also be seen in the precise calculations used in space exploration, where the geometry of orbits and trajectories is central to modern missions. The study of geometry also remains closely tied to Archimedes' work. Archimedes made significant contributions to the understanding of area and volume, particularly through his work on the measurement of circles, spheres, and paraboloids. His methods of calculating the areas of shapes using infinite series prefigured the development of calculus centuries later. Archimedes' ability to approximate values such as pi through geometric means laid the foundation for later mathematicians like Isaac Newton and Gottfried Wilhelm Leibniz, who developed the calculus that now underpins much of modern mathematics. Archimedes' work on the area of a circle and the volume of a sphere is still studied in schools today as part of the basic curriculum in geometry. In engineering, Archimedes' inventions, such as the Archimedean screw, remain in use even in the present day. This device, originally created to pump water from one place to another, has found applications in modern agriculture, wastewater treatment, and even in certain industrial processes. The Archimedean screw is an excellent example of how Archimedes' practical inventions continue to serve humanity, demonstrating the lasting impact of his engineering ingenuity. His other mechanical devices, including various war machines and tools, also illustrate his ability to apply theoretical mathematics to solve practical problems, an approach that continues to inspire engineers today. Computational mathematics, which is foundational to modern computer science, also owes much to Archimedes. His work on infinite series, specifically his method of approximating pi, laid the groundwork for later developments in numerical analysis. The algorithms he devised to approximate the value of pi were remarkably advanced for his time and foreshadowed the more sophisticated algorithms developed in the modern era. In particular, his methods were an early precursor to the development of iterative algorithms used in computational fluid dynamics and other fields. Archimedes' use of geometric approximations and iterative calculations has influenced the design of modern computers and software, which rely on similar mathematical principles to solve complex problems. Archimedes' profound influence can also be seen in the field of mathematical physics, where his work on hydrostatics, mechanics, and geometry continues to shape the way scientists approach problems in areas such as thermodynamics and quantum mechanics. His understanding of the laws of motion and equilibrium, for instance, is reflected in the principles of Newtonian physics. Archimedes' approach to studying physical phenomena through the lens of geometry and mathematics provided a framework that later scientists, including Isaac Newton and Albert Einstein, would build upon. His methods of using mathematical reasoning to describe the natural world are a hallmark of modern physics, where abstract mathematical models are used to explain everything from the behavior of particles to the structure of the universe. In education, Archimedes' work continues to be a central component of the curriculum in mathematics and physics. His contributions to geometry, calculus, and mechanics are fundamental to the study of these subjects. Archimedes' methods of problem-solving, combining rigorous logic with imaginative insight, serve as a model for students and researchers alike. His ability to approach complex problems with creativity and precision remains an inspiration for mathematicians and scientists in the present day. Archimedes' influence is far-reaching and enduring, shaping the course of scientific and technological development from antiquity to the modern world. His contributions to fluid dynamics, mechanics, astronomy, geometry, and computational mathematics continue to provide the foundation for much of modern science and engineering. Archimedes' legacy is not merely historical. It is a living legacy that informs contemporary research, technology, and education. His ability to blend theoretical mathematics with practical invention has ensured that his ideas remain as relevant today as they were in the ancient world. As we look to the future, the work of Archimedes will undoubtedly continue to inspire and guide the next generation of scientists and engineers. The life and work of Archimedes embody the highest ideals of human curiosity, intellectual pursuit, and scientific exploration. His innovations not only transformed the understanding of the natural world in his time, but also paved the way for future generations to continue building upon his discoveries. As one of the most influential figures in the history of science, Archimedes' impact extends beyond the realms of mathematics and physics, serving as a beacon for intellectual inquiry that transcends eras and cultures. His legacy is not merely about the specific theories and inventions he left behind, but about the way his approach to problem-solving continues to inspire critical thinking, creativity, and a deep commitment to knowledge. Archimedes was not only a practical inventor and a brilliant mathematician, but he also displayed an unwavering dedication to understanding the underlying principles of the universe. His work was grounded in a deep appreciation for both theoretical and applied knowledge. His ability to move seamlessly between abstract mathematical ideas and real-world applications is what sets him apart from many of his contemporaries. For example, Archimedes' famous law of buoyancy, which states that an object submerged in a fluid experiences an upward force equal to the weight of the fluid displaced by the object, became a cornerstone of physics that is still taught to students around the world today. This remarkable combination of theoretical insight and practical application exemplifies Archimedes' approach to science, an approach that places equal value on understanding the principles of nature and solving tangible, real-world problems. One of the most striking aspects of Archimedes' legacy is the enduring relevance of his work. Although he lived over 2,000 years ago, his ideas remain vital to modern scientific disciplines. From the discovery of the laws of buoyancy in fluid mechanics to the formulation of the mathematical principles that govern the behavior of levers and pulleys, Archimedes' influence can be seen in a wide range of modern scientific fields. Even in the contemporary age of advanced computing and space exploration, his contributions continue to serve as a foundation for new developments in engineering, mathematics, and physics. The survival and adaptation of Archimedes' work over such a long period highlights the universal nature of his insights and their applicability to problems that are still relevant today. In many ways, Archimedes' contributions have become an essential part of the fabric of modern science and engineering. His work on the lever, for example, is fundamental to the study of mechanics, providing the basis for understanding mechanical advantage and the operation of machines. The principles he established continue to be applied in the construction of buildings, bridges, and other infrastructures that shape the modern world. Similarly, his insights into the properties of spheres and cylinders laid the groundwork for later mathematical advancements, such as the development of calculus. Archimedes' approach to geometry, which involved the use of rigorous proof and logical reasoning, influenced generations of mathematicians and remains a cornerstone of modern mathematics education. Beyond his specific contributions, Archimedes' legacy is also a reflection of the importance of intellectual curiosity. Throughout his life, Archimedes sought not only to understand how things worked, but also to find deeper truths about the natural world. His unwavering passion for discovery, whether it was in the study of the relationship between volume and surface area, the calculation of pi, or the design of innovative war machines, serves as a powerful reminder of the human capacity for creativity and ingenuity. In many ways, Archimedes embodied the spirit of scientific exploration, always striving to expand the boundaries of knowledge and find new ways to understand the world. This dedication to the pursuit of knowledge has inspired countless individuals across generations to follow in his footsteps and make their own contributions to science. Archimedes' legacy also extends beyond the confines of academia and scientific research. His life and work have become symbolic of the power of intellectual inquiry to transcend the limitations of time and place. His contributions have been recognized and celebrated across diverse cultures and eras, from the ancient Greeks and Romans to the Islamic scholars of the Middle Ages, and even to the thinkers of the Renaissance and the modern scientific community. Archimedes' universal appeal is rooted in the fact that his work speaks to a fundamental human desire to understand the universe and improve the human condition. His commitment to learning, his ability to ask profound questions, and his relentless pursuit of answers have made him an enduring symbol of intellectual achievement. In addition to being a pioneer in mathematics and engineering, Archimedes was also a philosopher in the true sense of the word. His curiosity about the nature of the world around him led him to explore not only the practical aspects of science, but also the more abstract questions about the universe. In his writings, Archimedes frequently engaged in speculative thought, contemplating the infinite and exploring the nature of space, time, and matter. His meditations on the physical world helped lay the philosophical foundation for later thinkers, including Isaac Newton and Albert Einstein, whose work in physics built upon the principles of motion and gravitation that Archimedes had initially explored. This philosophical dimension of Archimedes' legacy has made him not just a great scientist, but a key figure in the intellectual history of humanity. Archimedes' personal qualities, his intellectual humility, creativity, and dedication to knowledge, further contribute to the lasting appeal of his legacy. He was not motivated by fame or wealth, but by a pure desire to understand the workings of the world. This intellectual modesty is evident in his famous declaration, "Give me a place to stand, and with a lever, I will move the world." This statement reflects Archimedes' deep understanding of the power of ideas and his confidence in the potential of human intellect to effect change. Archimedes' selflessness in pursuing knowledge for its own sake, rather than for personal gain or recognition, continues to inspire scientists and thinkers today. Archimedes' work also serves as a reminder of the power of interdisciplinary thinking. Throughout his life, Archimedes did not limit himself to one field of study, but sought to apply his mathematical insights to a wide range of subjects, including mechanics, optics, and even astronomy. His ability to bridge the gap between different fields of knowledge is something that modern scientists and innovators continue to strive for today. Archimedes' interdisciplinary approach is particularly relevant in an era where breakthroughs in science and technology often occur at the intersection of disciplines, such as in fields like biotechnology, nanotechnology, and quantum computing. Archimedes' example shows that the greatest discoveries often arise when different areas of knowledge converge and work together. Finally, Archimedes' life serves as a reminder that intellectual achievement is often the result of perseverance, hard work, and an unwavering commitment to solving problems. Archimedes did not achieve his greatness overnight. Rather, his legacy was the result of years of focused study, experimentation, and discovery. His ability to continue exploring new ideas and solving complex problems throughout his life is a testament to the value of persistence in the face of challenge. This lesson remains just as important today as it was in Archimedes' time. As we confront the complex scientific and technological challenges of the modern world, Archimedes' example reminds us that innovation is not always instantaneous, but often requires years of dedicated effort and a willingness to explore the unknown. In conclusion, Archimedes' legacy is a profound testament to the enduring power of human intellect and curiosity. His contributions to mathematics, science, and engineering have shaped the course of history and continue to influence modern research and technology. However, Archimedes' legacy is not limited to his specific discoveries, but also includes his approach to problem solving, his commitment to intellectual exploration, and his ability to inspire future generations. As a symbol of human ingenuity, Archimedes reminds us that the pursuit of knowledge is a lifelong endeavor, one that transcends time and continues to inspire innovation and discovery across the globe. His life and work stand as a lasting tribute to the power of human creativity and the unyielding quest for understanding.